Okay, hello. So today I want to try something different. So it's been a while since I've recorded something, and I read a bunch of articles recently on Hacker News about music, and I play music a little bit with my guitar, and I got excited with the music theory, the maths behind it, and I got this idea of trying to rediscover the reasons why there's like 12 notes on a piano, and why does it all work with by looking at the math behind the notes. So the first step is to go in a tone generator and look at what the tones are. Let me bring up a couple of those so we can mix tones. So we'll forget, like we don't want to mention anything about the actual notes like A, B, C, D and the actual numbers. We just want to listen to sounds and figure out the sounds that sound right. So let's start, like for example, 100. So that's 100 hertz, 100 beats per second, and 200 looks like this. So it's twice, and it sounds nice together. So that's an octave. And if we like just go to the third one, so 3 times, it also sounds nice with it, and like this. So when you trick is like on a piano, there's this one would not be there because it's twice this one. So we would jump immediately to 4. So that's the next one is actually 4 here. The same as this one. So if you include the 300, that's like the harmony, you would go with like 1, 2, 3, 4, 5. That's the harmonies of the fundamental frequencies. They all sound nice. So this one sounds nice with this. But it's not like the third octave. The third octave would be 4, and then would be 8. So if we go to 8, so that's going 1, 2, 3, 4, like 1 octave, and then another one to 4, and then another one to 8. That's the octaves. But let's forget about all this, and we'll try to really discover the actual numbers that we want. So for this, let's try something different, which is going to into a spreadsheet. Spreadsheet. And yeah. So we look at like a sign. Let's look at a sign. So what I want to do is to look at some graphic numbers. Let's start with this. We'll try to be like very specific about what we want to do. So I'm gonna say something like equal sign of some number. Like let's start with 0, and here I'm gonna have here like the dt like 0.1, and I'm gonna call this dt. So that's our dt, and here we're gonna say equal a sign of this number times an amplitude. Let's say the number that I'm gonna punch right here. Like we're gonna, well, not the amplitude, the frequency. I'm gonna put it here, and then time. The dt was time like the time. So, and here we'll say like 1. And now we have this. We could say here this number plus. Let's start at the beginning. I'm gonna say a frequency and see. Let's say. We'll try to change this frequency. This is the dt, and here we say this previous number equals this plus dt. Then we do that again a couple of times, and then here sine of frequency times this time times nothing, just like this. That's our I'm gonna just copy paste this here. Oh yeah, this. That is this. So that's our time. And now sine of this. B11. It's not B11, it's B10. And now, like, let's say I want to do a different frequency, like 2. And I want the same equation. So if I do this, that won't work because this one is the T got moved. It's using this, which is this. I don't want to use this, I want to use this one. So that's why before doing this, like that's a little Excel trick, you need to look at this color, like this B here, this B can't change when I'm gonna drag this around. So I'm gonna put this. The trick is to put a dollar sign in front of the B here. And now I can do this and this, and didn't work at all because I had to do the same thing with, let's do the same thing with this frequency here. Frequency was this C7, the 7 doesn't want to change. So that's my little equation for a sine that can have multiple frequencies, and then boom, did it work? Does it look like a sine? It goes up. Okay, and if I change the dt to a bigger number, it goes up quicker and then goes down. And this one goes up even quicker because there's this number in front of it. This D7, it's this. So now we have different frequencies. And we can actually look at those by doing, think, something like this, or just this. Do we know how to make a graph? Probably by doing this. Working. Oh, that's strange. Like, that was not what I wanted. If I bring in the first one, this, that's better. We see two signs. Nice. Beautiful. And we see, like, we already see what we wanted to see. Like, that's the whole point. We want to see that if I'm on a guitar and I put my finger here, we're going to have this note, this big fundamental note, but there's going to be a little bit of this one too in there. So when you pinch a guitar chord, you see all these harmonics. So I'm going to bring in one more. I think I can just do this. Let's see, 3 more. Oh, that was weird. So I'm gonna say something like this. And now, let's do that again. This. Oh, that's really nice. So I'm gonna need more lines. So let me do something like, weird, like, can I do like, yeah, I just squished a bunch of lines together. Now I can do this to get more lines. And let's try again. Maybe I should. Yeah, don't need this. Can bring this like this and pick up also the first line. So we can get, oh, yeah. Why does it go to 1 and 5? Yeah, the first line should be the index. Use columns B as labels. No. Yes. Use Yeah, maybe I don't want to kill this again. Delete. I'm gonna use this again. I don't know how to make graphs, but we'll figure it out. Oh, this TT is bad. Let's take one. Nice. Wow, beautiful. More. 0.4. 0.4. 0.5. Nice. That's exactly what I wanted to see. Because I want to see what a guitar chord is doing. So there's all, if you put your finger here, you're gonna see all these modes of vibrations, and you're gonna try to recognize the sound. You're gonna know if it's a voice or a guitar or a trumpet by looking at the ratios of each of these harmonics in the chord. And that's where we start. Like, that's the starting point for music. It's understanding that there's all these sounds mixed together in any sound, and that's what the brain is trying to do. The brain is trying to decide what you are hearing by figuring out the ratios of each of these harmonics in the sound, so that you can know if it's your mother talking or a wolf or a cat. So, like, that's the evolutionary advantage of being able to understand sounds. So that's what the brain has to do. Like, the goal of this video is to figure out what equations the brain have to do to understand who's talking, so you can recognize your mother among a groups of person, and that's a strong evolutionary advantage of being able to do that. And maybe being happy by when music like resolves to the fundamental and the home sound, like the bass sound of a song, like at the end of a song, when you go back to the note and like that resolves to this note, and it's really satisfying. It's because the brain like discovers that what he's been solving this whole time, like it's like getting to the solution, and you get this rush of endorphin because like you found the solution somehow. So that's a theory of why it's satisfying when music resolves. It's because of the math of the brain trying to figure out which one of these are in there. So let's look at this more carefully. So what we want to do now is to, like, the notes are like in there somewhere. So like let's say let's forget about this one and this one, and we'll just look at these. So this is 2 times more high pitch. This is 3 times more high pitch. But as we said, like this, the one that's 2 times higher, it's like the same. In our brain, the first thing that happens in the brain, the first thing that you need to do when the brain has like multiple parts, but there's the first thing that happens is each of these modes gets decomposed, and you see it in the frequency space. You see like each frequencies, how they're represented in the sound. The first thing that the brain tries to do is to clump together all the ones that are like a factor of 2, like a power of 2 together. So it means like when you see a sound, you can divide it by 2 or multiply it by 2 multiple times until you get close to a range that your brain can understand. So that's every time you have a frequency, you can multiply it by 2 or divide it by 2 to get in the range. And so that means that the second one is just actually the same note. So the blue one and the red one are actually the same. But the third one is not the same. So it's a different note. It's just the third harmonic, but it's not an octave higher. So the brain, the first thing that it has to do is to bring it closer. So in this case, it's like 3 times higher, but we want to bring it back into between 1 and 2. So every time we have a frequency, we want to bring it back between 1 and 2. So this 3 is bad, it's too high. So we need to divide it by 2 until it gets between 1 and 2. So 3 divided by 2. So that's stupid. Format number, please. Always numbers. And I would say equals, yeah, 3 divided by 2. That's our first like real note. So the goal now is to discover the note. So we have 1, like that's our first note. Like, so here it's going to be, let's say it's 1, but let's say it's 100, so it's easier to hear. So that's our first note. Let's call it note, our first note. Okay, that's we have this note. We know we want this to be our base. So the second one will be 2. Like we want 2 also. It's 2 times this, so we're going to 200. So we have this one too. And all our notes will need to be in between these two. And we want to find the ones that sound right. And that are consonant, so that means like if there are too close or like weird ratios, there's going to be some beats. So maybe beats is another subject. It's like how it, so there's 2 theories. Like so some people say two notes together. Yeah, like it's actually the same thing. If there's beats and it sounds bad because there's all these places in time with like big with at low frequency beats because they're too close and they go together or cancel each other so we could actually try to see the beats. Let's look at the beats by just listening to it instead. So if I do 100 and just a little bit more here, so with this, those are the beats. So instead of explaining it, so when there's beats, it's really bad. We don't want these 2 notes together. But as soon as we get problem, maybe like this might be too loud, and let's not be too loud. So let's start at 200 instead, and we the beats itself, it's feels as if it's not enough to decide if it sounds right or not, because beats happens only when it's really close. Yeah. Ouch, sorry for this noise. So we're gonna keep this one. So that's 1.5. We know it's good because it's this third one, but divided by 2. The other thing we can do is to actually start with the 1 and like divide it by 3 instead, and going to 0.33, but then multiplying it by, so I did the simplest thing I could do here. In this case, what I did is times 3, but then divided by 2 to get into the range. Here I'm going to do another, like the simplest fraction you can do. So I'm going to divide by 3. So the simplest thing you can do with the smallest numbers. So we need to go to 3 because if I just multiply and divide by 2, I stay with the same sound. It's the octave. So the simplest thing you can do is multiply by 3 or divide by 3. But we want to go back between 1 and 2. So I divided by 3 here, but I need to multiply it by 2 a couple of times until we get into the correct range. So I'm going to say times 2. And I need an equal sign. And I'm still not in the correct range. So I need to do times 2 again. Times 2 again. Boom. And then we get to this. So that's a number that is in the range. So using only the number 3, like the simplest thing that is bigger than 2, we get these 2 new notes. So now we have 4 notes that are in the range 1, 2. And so that's notes that we know that will sound good. And that we can start building our instruments by using the ratio 1, 2, 1.5 and 1.30. So those are like maximally close in terms of like small fractions, because we just multiplied by 3 or divided by 3 our basic frequency. So that's one thing. So we could also like look at just simple fractions. So one way to look at simple fractions is just to say something like 1, 2, 3, and yeah, so and then here 1, 2, 3, and continue like this. And also, and here we say like 1 divided by the other. So I'm gonna say equals this divided by this. And I need to put my little this one, the number of the row will not change, and here the column will not change. So if I do this and this, it failed because I did not do the correct thing. It was the opposite, because you can't get it right the first time ever. So I just do the opposite. So it means that my equation will try to keep the column constant here for the first number. So like this, 1 divided by 1, 1 divided by 7, and here it looks like this. So those are the simple fractions. But we just want the ones that are between 1 and 2. So I can do something weird like saying I want to be equal to if the number is between. That's a thing. Yes, is between. Like, so this number is between lower value between 1.01 and 1.99. Just because we know we already have 1 and 2, we don't want to see it again. Don't care. So that's bad. So what to do when, if between, I want to see the number itself. I want to see the number. Or else, if it's not between, I'm going to keep 0. So this number was, so I'm going to do something like this and this. Yes. Yes, that's what I wanted to see. So those are like the simple fractions. So when people in with like between 1 and 2, the simple fractions, it's those. Like these are the simple fractions. It's this, this, this. We already saw this one. This one is this one. We didn't see this one. So it means that it looks, so it's simpler. Like the simplest fraction is this one. Then we have this. And then we might want to investigate if this one sounds nice, and those. And then we go here. And we have more fractions that are a little bit more complicated. So we can bring this, yeah. Can I just bring this and this? So we see our nice fractions. But then there's this other thing I want to do. Like, let's say you have this note and this note. So what happened is, what we did is to just start with 1 and say this number times, we say 1, and we say equals 1. This number up top, and then just times 1.5. And that gives us another note that we like. And if we just do it again, it just gives us more and more notes that we're gonna like also. And it's gonna bring us like the punch line is that this is the circle of fifth if you just do that over again. But yeah, so we go here, and then we get more and more, and you can continue going in circle, and you get more notes by just always multiplying the pitch by 1.5. But then those are too high notes, and what you want to do is to divide them by 2 until you get in the range. So we're gonna, like, you could divide it by 2 here, or divide it by two times. So let's say equals this number times 2 again, and then times 2 times 2 times 2. So this is what happens if you divide, multiply, that those are the powers of 2. And what we're going to do with this circle of fifth thing, we'll want to go back into the range 1 and 2 and see what happens. So we're going to just divide it by these numbers until it's in the correct range. But let's not worry about the until part and just divide it by this. So I'm going to just say here equals this divided by this. Whoop. This divided by this. And I'm gonna do the little thing that I need to do with, because I'm gonna go drag this. So for this number, I don't want the line to change. So this 101 can't change. So I'm gonna put my $sign book. And then here it's the column C that doesn't want to change. So I'm gonna put my $sign here. I suggested autofill, okay. So this is the numbers here that all just 1.5 of the number in front and then divided by 2. This divided by 2 gives this. And I'm going to just do the same thing here. That's divided by 4. That's not what I wanted. But yes, that's what I wanted. It's always the first column. So we're not using the column in front. So it's really this number, this 5 divided by 4 gives this. So I hope this is clear. So I'm going to do this. And now, some of these numbers will be between 1 and 2. And those are notes, the circle of fifth that we just discovered. And we get the notes that we want. And they're like, we just went with some, like, it's going to give us always more notes. It's going to fill the space. The interval will be filled with more and more notes. Like, we don't know how far it's going to go. One fun thing that could happen if we're lucky, like, spoiler alert, we're gonna be lucky, and that's the fun thing that I was thinking about, like how lucky we got by, like, there's a number like the 12 thing. It's just pure luck, like math number. Like if you do 1.5 and multiply it by itself a couple of times, you see what happened. Like we already see the luck. The luck is that what happens is that you get really close to one number that's really spooky. How lucky we got. Look at, there's one number that's very different than the other. Look at this guy here. And that's the punchline of this whole presentation, is that this number is very close to another number that is on the page now. And it's this number here. And because of that, this number here is very close to 1. And this is the punchline. We found a number here that is 1. It's because we looped around the circle of fifth and we went back very close to the beginning. That's how lucky we got. So I'm going to do the same trick as that I did here first, just to see the numbers that are interesting in here. So I'm going to do something like equal if is between this number between 0.01 and you can't see what I'm doing. I want to, what? Oh, let me stop. If is between this number between 0 is 1, let's say 1.999 to get all of them, is between, I want to see the number. Why? I said I want to see the number. Why? Come on, the number L0. And I'm gonna do this. Took and magic. It's beautiful. We see all the numbers that are between, and we see our, like, that was the whole. Why is this number not there? Because I forgot to bring in this. Oh, okay, let me kill this line. We won't go that far. And I'm gonna do something like this. Yeah, we have this one that was missing. We have our numbers. It's beautiful. So what do we do with these numbers? So that's all like notes that happens when you do multiply by 1.5 and then divide until you get back in the range. So what can we do with this? Okay, let's move this to the side. Oh, not. Maybe I could bring it down here. Yeah. And now what I want to do here is, so we see our magic number here, but let's let's trust that this guy here is actually, we already have it. It's this. And this is just a repeating of, it's almost repeating the other one. So let me like decide, we're looping around, we don't care about this. We don't care about these columns. And also we don't actually care about this one because it's this yeah, this one, yeah, between. Okay, we can keep this one here. And this is actually this, so maybe we don't actually want that, and we trust that we don't actually care. So we're gonna just consider these lines, and what I want to do is like bring in these numbers all here in one nice little column. So I'm gonna do the trick would be just to equal sum, like the sum of the line, the sum of this line, sum of the line, sum of this line. And if I do this, I see all my notes that I just discovered with the circle of fifth. I'm gonna go just up to here. Let's forget about the last one. And we have these little numbers here. And now we can investigate, like, what do we have here? So the first one, we already like decided that we like these numbers. Let's bring the numbers that we like close. And we also like these. So let's see if we're ever even more lucky. Like it felt like this is the first bit of luck that we got. Like it loops around when you do times 1.5. After 12 times you did that, we got really close to a number that was here. And like it was not clear like that like how lucky we got, because these other numbers, like maybe it's not like pure luck. Like if it looped around here, like the 38, 32, so it could have hit before or a little bit after, but this 12 is really magical. It just happened just to correct, like it did something here. One thing that we could look is like, what are these numbers? Like let's look at them first. So I'm going to just do like, please show me these numbers on this. Oh, this is it. This is what happens with the circle of fifth when you make it loop around between 1 and 2. Interesting. Chart style, setup, line chart, better. Scatter, okay, scatter is better. So let's look at these. If we squish them, like something here, like this is it. Like the other, like there's three, it loops almost perfectly. Then it just happened that they like went and just filled a little bit the vertical space. Is that like weird to you? Like that for me is like spooky. Spooky that like there's one here, here, here. They're all like almost equal vertical distance. And that's the magic with the scale. These 12 notes already almost equal. we could just tweak them to be exactly equal, and that's the normal tuning of a piano is equal distance between the notes, but it's almost already good. And the other piece of magic is that these numbers that we like wanted, because they're special ratios, also come close. So let's look at like this number here, this 1.33. But we didn't actually like put it. We started at 1 to get to the 133 before. What we did is go backwards with this, trying to guess the number that is lower, that goes when you take the perfect fifth forward, you get to the root note, and that gave us this number, but it's close to the last one. So yeah, it's the last one. So it got close to this. So we got this nice number. Let's put it in bold. Like, we like this number because we want it, and it's also like for the same reason, because of the little math that I did, is that it's actually 4/3. So it's this 4/3 here. 4/3. It's this number that we got here at the end. So this number we like. This number we like. And we said we like this number too, and in the 2, and that's it. But is there other numbers in there that look, by pure chance, they look like there are numbers that are here? So, but this is very like just luck. Like, let's like this one. Is there a number in there that looks like 1 point? So let me copy this here. That's a number. Oh. Can I copy the value, please, of this? No. I'm gonna just say 1.666. That's a number we like. Is it there somewhere? 1.666? Yes. It's close. It's not perfect, but it's close. This one is close to this. And we're close to the beginning also. So when it's close to the beginning, it means that like there's a big relationship between these. Then this one is what happens when you just, it's a simple fraction too. Like, it's close to which one? No, and this one is not as small as the other ones. So it's not this. It's too far from this one too. So it's not in there, but it's still just the 1.5 times, this was we just did it twice. It's just 1.5 multiplied by its 1.5 again, and then divided by 2. So that's what happened to get to this. So it's not a very complicated fraction. So what this fraction is actually is 3 times 3 divided by 2 times also, divided by 4. No, I didn't divide it by 4. It's divided by 8. By 8. Why? By 8, I said. Yeah, so this fraction is actually 9 divided by 8. So it's not really small, like in simple fraction, like going for 9 here. So 9 divided by 8. It was too far here. 9 and 8. So it's actually, yeah, we could continue and say 8 here. And copy paste this. Why? Because we forgot to continue here. Yeah, so it's right here. It's far. But okay, we like it because it looks far here, like 9, 8. What? What? 8? 8? It's bad. What? Confused now. I'm confused. I'm trying to understand. It's still 7 here. That's better. It's here. So yeah, we don't want this one. We want this. This one, we like it. we put it in bold, and we also want to put it here. 1.35, 135, 125. No, that's not the one. Yes, that's the one. Okay, so it's here, so we like it. We said that we like this number, so we have notes that we like, and it's the first one. Then we go to the one, if we blow it back again, so we see the order. What happened is 1.5, then 1.125 is this one, and then 1.658 this one. So this chance. Okay, so let's continue. This one, we already said it's this. So is there other ones? 125. That's a simple fraction. That's 5 divided by 4. 5 divided by 4 is really small ratio. So like there's going to be no dissonance. It's really no beats. Like these two notes are nice ratios. So it's right here. It's right here. Look, we like this one too. And then 175. Is that there somewhere? This one is sad. The first one, like that, we're like, oh, it was a simple fraction of sorts, 7 divided by 4, but we don't see it in our circle of fifth. There's nothing really close to it. Yeah, so that's our like first time we're like, this ratio, we don't get it. But this one, 1.2, right here. That was this 1.2. It's 6 divided by 5, so not too bad. 6 divided by 5. Small ratio right here. Get it. Nice. Okay, so let's forget about this. We're happy with, we don't want to, maybe 1.4. Is that there? 1.4. Yes, it's here. Ooh, like it's also like let's continue. 1.6. Is it here? Yes. So this really feels like luck, because these ratios are not the ratios we used to go to that. Like what we did is something different. These ratios, this equation is not at all the same ratio. It's not the same number. Like you see, this 1.201, 1.2. Like there's a mistake. It's just by pure luck we got really close. Like 1.8. Yes, this one is there. Boom. So only this one and this one are not very close to things we really like. But anyway, so we got this, and now the next step would be to sort this. But let's just sort it and say equals sort. Sort. Is that a thing? Probably. Sort arrange. Yes. Let me sort the range. Oh my god, that's so annoying. Sort equals sort this range. Yes. Yes. Sort. So we have our notes that look like this. We can also plot this, I guess. Let me plot this directly. Look. Wow. So we have the line that comes from the circle of fifth directly. So you see, it's not really like, it's not perfect. There's little jitters. It's not a straight line. Now the other line that we want to do is, let's say we want it to match actually. So we want to make another column here that's going to start with 1 and finish 2. But with constant ratio increment. So we want to multiply 1 by some number. We want to multiply it by some number to get this number. And we want to multiply by the same number to get here. So what we want to do is to multiply some number, okay, some number, my number, mystery number, if I multiply it by itself 12 times, I want to get to 2. So I'm going to say like exponent 12 times. I want it to equals 2. So that's like, let's find a number that when we multiply it by itself 12 times, it gets 2. So that's the definition of a 12th root. So for this, we need to go here and say 12th root. So I'm going to say 12th root is like, I don't actually need to go, I'm in the spreadsheet, so I should just say 12th root. So 12th root is actually, is that a thing? Root? No, it's power. It's exponent, and exponent is this little symbol. So I'm gonna say the 2 to the is this, I guess. And now what I want to do is square root is like power half. So 12th root is 1 over 12. So that was the trick. That was the hardest math part here. Like, we're trying to find a number that we're going to multiply to get to 2. So the trick is to do 2 to the 1 over 12, which is the 12th root of 2, which is this number. So if I multiply with this, this is a magic number. Let's just remember it. It's 1.0594. Okay, so that's an important number, because I'm going to just say this, and I'm going to say that here it's going to be the number before. Oh no, what I want to do is, yeah, it's here. Like, I want to actually do equals the number before, which is 1, times this magic number here. And you see, we're close to this, and that's equally tempered. This didn't work. Yes, it worked, because here, boom! Yes, beautiful. It worked. So we don't actually need to go to the, like, we trust, like, we're happy with this. So those are our 12 nodes with equally tempered. And we see the error that we're making. You see the error? What's the error? The error that we're making equals this minus this. No error for the root, and then some errors, and this, what we want is here. We messed up the last one. We don't know the error for the last one because we didn't keep it. So yeah, let's keep it. This number. So here we want to sort, but let's change the equation for the sort and continue up until 36. So we see the octave here. 1.1, it went here, so that's why we didn't like it there, because it went bust. It went around this one, so maybe that's why we don't actually want it. So let's kill it. And we won't actually see the error that we're making at the last one, because it's the difference between this number and this number. That's the error what we do at the octave. If we want to just do this. But it's not really an error that makes sense when you're at the end of the circle of fifths. We don't actually care about this error. It's the ratios between each possible intervals between all the nodes. So what do we actually want to see is this error, like here, the 2 lines. So can we do that? That would be nice to see. Not before that, we could investigate these numbers. So this 1.5, really small error, and that's why we're really happy, because our most important one, like the perfect fifth, is a really small error right there. This one also, really small error. Some of them have bigger errors. So which one has the biggest error? Like this one at the end. So that's the minor 7th. Minor 7th has a big error. Also this guy here. That's the one. That's the perfect fourth. That's the fourth. That's the third. So I'm saying the words now, like we can actually name these, like these. This is the root note. This is the major second. So that's the first tone. That's the semitone. That's the semi. That's a major. Let's put it with a big M. That's the minor second, which is a semitone. And now I'm saying the words that I said that I didn't want to say the words because we don't actually care about the names of these intervals, but like everybody always mentions these intervals, so that's a tone. And then we have the minor third and the major third, and then the fourth, like perfect fourth. We say perfect fourth. There's here the tritone. All these intervals have names and books written about them. There's many songs that just insist on this interval, and then there's whole YouTube videos that show like how you can recognize this. So for example, this one, the perfect fifth, that's the Star Wars theme, ta 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 na 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 ta ta, and this is Frère Jacques, na 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 ta na na. And then like all of them like has like are the first two notes of songs, so you can recognize them easily. Anyway, you can Google. Look, I could show you on YouTube. Like, there's a nice video that explains how to recognize each of them. Anyway, so now we're at the minor sixth, and then the major sixth, then the minor seventh, and the major seventh. And in the if you want to go in C, and you see it's the major C, this. Let's move this a little bit. This is C. This is C sharp. This is D. This is E. This is F. Perfect fourth. The tritone is F sharp, and then perfect fifth is G. And then A and B. So, do, ré, mi, la, do, ré, mi, fa, sol, la, si. But we're looking at this and we're trying to see the error that we're making. But now we have like a better understanding of these numbers, and we know like which one we're most happy with. Like the one that we were not really happy with is this 89. Yeah, because it's really not there in the small ratios, but it's close going. It's yeah. And then this one, that's our semitone also. Like it's really like not a small ratio, but we need it. Like it's close to the mystery number, so we're happy. It's gonna be our first guy here. Okay, so what we wanted to do is to let's what we want to do is let's move this error. Like it's the difference between these two numbers, so let's put it in between. So difference. So that's what that's coming from a circle of fifth, and this is coming from our mystery. No, this is coming. No, this is not from the circle of fifth. This is like equal tempered using our little equation with the magic number, which is this square 12th root, and this is coming from sorting this array that came from this. And this is the difference. This is the error that we're making. And this is by sorting the circle of fifth. And what we want to do is look at, let's kill this one and look at this and this, make a graphic. of this. VS equal tempered. Oh, I don't want VS. I want them to be like a series. Combined ranges horizontally? No. Data range series? Yeah, I don't want that. I just want one of them. I want one of them like this, and the other one, I'm gonna add a series and click here and give me this and say okay. And then we can look at the error that we're making when we are doing the equal tempered thing. So when you're a piano tuner, if your job is a piano tuner, this graph is interesting. Like you see the actual errors. Equal, tempered, where is it? Oof, we don't see which one is which. Can we have like the legend series setup? Use column K as labels? No. Use row as headers? Yes. One? No. Yeah, that was bad. So let's kill this again and start with this. And then add, yes, equal tempered. Nice. And then I'm gonna add a series, click here and bring this like this and say okay. And then we see the two things we wanted to see. And this is the bottom line. We see our nice little numbers. So the blue ones are equal ratio. So this is some like this is a big ratio, but it's the same ratio. It's just bigger distance because we're higher. But all the blue ones are the same ratios, and the red ones have little errors. But you see, not too much errors here. For this one is important, and this one, the third. So first tone, second. So the third, we're really lucky, and the fifth, very lucky also. But this is very strange and spooky that math just aligned. That for me feels very magical. I don't know why. It's very mysterious. This one is bad. That's why maybe like music is really don't like when you go to the minor seventh, it sounds nice because the ratios work well with the others, but it felt like it's a big mistake. But anyway, so what would be the next thing? Maybe we should plot like these nice numbers, like because some of them have a nice number attached to it, like that looks like a nice number. So like for example, like we said, there's like the nice ratios. So there, some of them have like this 125. It's not there. Like 1.125 right here. So I can add this here. So I'm gonna add nice setup, add a series, and bring in the nice ratio. Oh man, are you kidding me? No, no, no. That's add series, bring this guy. Oh my god. Select arranged. Okay. Select this. And I'm gonna say okay. And the nice ratios here. You see, this one, it's pretty close. But other ones, like this 6/5, that was which one? It was this? Yeah, this minor third. This minor third, like this 6 over 5, it's just pure luck. Like, let's just say equals 6 over 5. This 1.2 equal exactly 1.2 instead of this or this. So by sorting the circle of 5, we get this, which is close, and then the equal tempered, bigger error. So we see here, this error that we're making is closer to the red one, which is the 5. So if the three things, like small ratios, equal tempered, or sorting the circle of 5 gets really close, it means like we're so lucky, very lucky. God, we got lucky. And what are the other numbers? Like this guy, 1.33. Where is it? Exactly 1.333. It's this dude here. It's much closer than the equal tempered. So the equal tempered really is closer than what happened when you sort the circle of 5. This is the perfect 4. This is tritone. So maybe we could draw things. Can we draw things? Let's continue and just bring in a couple more. 125, is it there? 125 is this one. 1.25. This one. And the other ratios that we wanted to see is 1.666. 1.666 looks like this one. 1.6666. Oh, this one is far. So the nice ratio is far from sorting circle of 5 and equal tempered. So that's our major sixth. Can we draw things? Like put things? Legend for the points. Series. Can we just like add this? Add a series with... I don't think we can draw things really. But let's finish with what did we forget? This 1.4, is it there somewhere? Yes, 1.4. It's a nice little ratio. Was this guy really far? So maybe we don't actually care, like the fact that this ratio exists. Like this ratio looks small, but it's not that interesting. It's 7 divided by 5. It's yes, 1.47 by 5. Yes, this is exactly 1.5. 1.5. We got very lucky. Like the red, the 3 points are exactly there. This one is actually exactly there. This one is not. 175 is that one, the one that we didn't know what to do with. Like 175 is just meh. We could still write it like that's a fun little ratio, but it went here. Meh. So that's just sad. Like, don't really like it. So maybe we don't care about this ratio. Let's kill it. 1.6, is that a thing? Yes, it's a thing. But not really. Like, it's really close to the other one there. So it just went here. Oh. It's not too bad. It's right there with this guy. No. No, it's this. It's this 1.6. It's the minor sixth. Yeah. So that's it. That's the little experiment I wanted to do. Looking at this. But like the punchline is really, we got lucky here. We got lucky that these numbers show up here. Just pure luck that 12 worked so well. So that was the point. Okay, bye.